Okay, chapter 14 is digital technology. Basically, three main topics that will be covered in this. One is analog and digital signals. Okay. Second is about how compact discs work, CDs, and the third is CCDs. These are the most important points over here. So, firstly, analog and digital, the first part is conversion between binary and decimal, and conversion from decimal to binary. This is very basic and it should be understood by the students. So, things that they need to note are what is the most significant bit, okay, what is the least significant bit, and what's the consequence of a least significant being 0 or 1. Okay, so they need to be able to identify that. Binary to decimal conversion and decimal to binary conversion is something they should be familiar with from computing, or else you can probably go through with them what the method is. Again, some schools also go from binary to hexadecimal, but that is not in the syllabus. Okay, so you don't need to worry about that. Okay, analog and digital, they need to know what are the advantages of storing information in digital form in terms of reproducibility, storage capacity, portability, etc. All this is covered on page 5. So this is a little descriptive, and you can actually go through with them. On page 4, okay, so that's pretty much the first portion. Second portion is about CDs and how CDs work. Basically, in CDs you have a series of bumps and pits, okay? And when you have a bump and a pit, there will be laser lights, okay? Two laser lights which will be shown on the top of a bump or a pit, okay? When the laser is shown in this form, on both of them being shown, both of them reflecting off the bump, they will be received at a particular receiver over here, and these two laser lights, mind you, are coherent sources. So when they are received over here, there will be constructive interference, okay, and that will be received at a particular signal, either 0 or 1. Okay. From what I have understood is that constructive interference is actually a signal of 0. Okay. Whenever we need a 1 or whenever we need the opposite signal, what will happen is one of the lights will reflect off the bump and the other one will reflect off the pit. Okay. Now the path difference would be approximately this much, okay, which is 2 times the depth of the bump or the pit. Okay. Now this path difference should be equal to lambda by 2 if we need destructive interference. Okay, so we will have destructive interference and we'll get the opposite signal over here. Okay, so therefore lambda by 2 is equal to twice the depth of the pit or the bump. Right, therefore we have the depth equal to lambda by 4. Okay, so this is the relation for CDs. In CDs, other than this, they need to know what is meant by some of the terms of CDs. The dimensions, we have the bump width, we have the length of the bump, and the depth of the bumps as well. So the depth is here, right? So they say that the depth is about 150 nanometers deep, which means that the light that is shown, the laser light, is of wavelength 600 nanometers. Okay. Then what they also need to know is the track separation. The track separation is usually about 1.6 micrometers. Okay. So keeping in mind the track separation and the width of the bumps, etc., the student should be able to use this information in order to determine what's the total number of bits that can be stored on that entire CD. Okay. And then there can be questions which ask, like, if so many bits are required per second of music, then how many minutes of music can be stored on a CD? So this is the kind of problem solving that they would need to do. Now, the difference between a CD and a DVD is essentially the track separation. So you can read at the bottom of page 4 that the DVD pits are about 0.44 micrometers in diameter as opposed to 0.5 micrometers in CDs, and also the track width or the track separation is 0.74 micrometers as opposed to 1.6 micrometers in a CD. So just basic dimensions of CDs is what they need to understand over here, and this concept of constructive interference and destructive interference to receive two different signals. Okay. There is also a part which may not be in these notes over here about sampling rate and quantization of signals, quantization or digitization of signals, right? So over here you should know that when we have, for example, an analog signal, okay, and it needs to be converted into a digital signal, we will select levels. Okay, the number of levels or the number of digital levels will depend on how many bits of information are we using. Let's say we are using 2 bits of information. So the lowest level will be 0, 0, then we will have 0, 1, 1, 0 and 1, 1. Okay, so these are the 4 levels in which I can store this information, right? As you can see, this is not actually enough because the maximum amplitude is going above the level over here. So what will happen is that these levels will be spread out further. Anyway, depending on the sampling rate, if the sampling rate is high, then we would have the samples closely spaced, okay? And if the sampling rate is low, then we would have the samples further spaced apart. So you can see that it is beneficial for the sampling rate to be high, okay? And these are called quantum levels, okay? So we want 2 things in sampling. We want a high sampling rate, okay? And we also want a high number of quantum levels. Quantum levels depends on the number of bits being used. Okay, so we want this to be high as well in order to reproduce accurately the original analog signal. Okay. Okay. The next portion is charged coupled devices. Charged coupled devices are basically sensors. It's a sensor which is installed in most DSLR cameras. So this sensor is a series of capacitors. Okay, a capacitor basically is a device, electrical device which can store charge. Okay, so you have this is what defines the capacitance. A capacitance is defined as the amount of stored charge in a capacitor divided by the potential difference developed across it. In essence, a capacitor is simply 2 conducting plates with a material called dielectric in between them, which allows for the charges developed on each of these sides to interact with each other. Okay? If there was no dielectric, it will just be a broken circuit. But since there is dielectric material, this is a capacitor. Okay? Now the capacitor has a measure of the capacitance is the capacitance here, which is Q over V. Q is the charges stored and V is the potential difference across the ends of the capacitor. Now this is measured in farads, okay? Also just written as F. And since 1 farad is a large quantity, we would generally be dealing with PF, which is picofarads, which is 10 to the power minus 12 farads. Okay. Now, so a charge coupled device is basically a series of these capacitors. Okay. When the shutter on a camera opens, basically what happens is this is a metal, just like we discussed in the photoelectric effect. The metal plate on top, okay, when the shutter opens, light falls on this metal plate, and the photons will eject electrons, okay, on the surface over here of the capacitors due to the photoelectric effect. Okay, so we have photoelectrons ejected at the top of the metal surface on each of these capacitors. So there would then be some charge developed on each of these capacitors, and due to the capacitance we would have a potential difference across each of these capacitors. Now the potential difference which has been developed across each of these capacitors is proportional then to the charge that is developed, and therefore is proportional to the intensity of light which falls on the capacitors. Okay, why? Because more the intensity, more the photons, and therefore more the electrons that have popped out, and therefore more charge that is developed. Okay, now in the notes you will find that we are not just talking about electrons, but we are talking about electron hole pairs. Okay, a hole is nothing but a positive charge developed when an electron is separated out from the surface. So greater the number of photons incident, greater the number of electron hole pairs created. You can see this at the bottom of page 6. So again it mentions that the number of electron hole pairs produced will be proportional to the intensity of the light. Okay, so when we have a series of potential differences created across each of these capacitors which is proportional to the intensity of light, this signal is then digitized, okay, and this digitized signal is then sent to an intensity map. Okay, so the intensity map notes the position of each capacitor and the voltage level on each of those capacitors, right? And this is then displayed on the LCD screen on a camera, for example. So then on the LCD screen you will be able to see a reproduced image of whatever this CCD had captured when the shutter was opened. Okay, so that's basically how the basic working of a CCD. Now, so it works pretty much like a photographic film, except that the data is in digital form over here. So the students should be able to use this formula for some numericals, and some of these numerical examples are given later. Firstly, a few more details regarding this.